Do you see my screen?
Great. Yes, go ahead.
Okay, thank you very much. So welcome everybody. I'm Timoteo Carletti from Naxis, the Number Institute of Complex System in Belgium. And I represent some work about a random walk on a hypergraph. This is a joint work with some colleague of mine that I would like to thank. I also thanks the organizer for inviting me. So in the last 20 years, we observed the explosion on network science. Indeed, networks are a very general framework where to model different kind of systems. They can be a social system, physical system, and so on. The idea is that you identify the basic units and you call nodes. And then if two nodes do interact, then you put a link between them. So you can think, for instance, of networks where nodes are the authors of a papers, and you draw a link if two authors have written a paper together. So this is a co-authorship network. Once you have a network, it is important to realize there is a strong interplay between dynamics and the structure. So once you run a system on the top of a network, the dynamical outcome of the result will strongly depend on the structure of the networks. That is, how links are connected, how nodes are connected. But at the same time, you can use the dynamical system to unravel the structure of the network. And so, for instance, so to study this kind of interplay, a simple but largely used model is the random walks. In the simplest case, random walks are processes where you have an agent, a walker, that jump among nodes in the network using the available links. Then in the simplest case, you can prove that the stationary probability, that is the frequency that a walker visits a node, can be computed explicitly and depends on the degrees, that is on the number of neighborhoods of each node. You can use this random walk process also to rank the nodes. You can rank at the top the nodes that are visited much frequently. So the top rank node are the ones that have largest degrees in this case. And also, so if I think again in my example of authors that are nodes and links, if they're written paper together, you can rank authors by how often they wrote paper in collaboration with other colleagues. However, the example that I just introduced is also gives you also some limitation of the networks, because in many cases a network can be used to model only pairwise interactions. But this is not the case very often in nature. For instance, this is not the case in the co-authorship network, because very often papers have more than two authors, and so you cannot distinguish using a simple network if you have a paper with three authors or three papers with two authors each one. And so to go beyond, so if you model this network using the network, you can obtain a ranking which is not the real one, because you lose some information. So to go beyond this problem, we decided to go beyond the network structure, and so to introduce the hypergraphs. Hypergraphs is a generalization of networks where now nodes can be connected in groups or arbitrary sizes. So you go beyond the pairwise interaction, allowing groups called hyperedges to have any size from 2 up to whatever you want. Just to fix the notation, you have an incidence matrix, EI alpha, which is 1 if and only if the node I belongs to a hyperedge E alpha, and then you can compute the hyperadjacency matrix, or the complementary view, the hyperedge matrix C, and where C alpha beta is the number of nodes that are shared between hyperedge alpha and beta. And so in particular, the diagonal of the matrix C give you the size of the hyperedge. So the idea is to extend the random walk process on this kind of hypergraph. Here we start from the following idea, that if you think again of the network where your nodes are authors and papers that write papers together, here hyperedge is a paper, and all the authors that wrote the same paper are part of the same hyperedge. So in this framework, you can think that the knowledge among the authors spread faster, or if you want better, as the function of the size of the hyperedge, and thus we define Kij, so the rate such that the agent jump from node I to j to depend on two quantities at the same time: the size, C alpha alpha, and the number of shared hyperedges, the incidence matrices E I alpha and J alpha. There is also a parameter tau, because you can think that the larger the size, the better is, so tau is positive, but you can also have some models where this is opposite. So if you take tau negative, then the largest size reduces the speed of the spread of the information. Here in the following, I will take tau equal to 1 just to simplify the things, but if you're interested, you can look in the paper that are quoted down in the page. Once you have this matrix K, you can compute the matrix L, and indeed you can prove that it's a Laplace matrix, which indeed generalizes the standard random walk Laplace matrix for networks, and then you can, so it has an eigenvalues equal to 0, and then you can compute the stationary equilibrium, Pi infinity, which depends on this quantity Kih, which is the hyperdegrees, which is a quantity that generalizes the degrees. It takes into account at the same time the size of the hyperedges, but also of the number of incidence hyperedges. So so the dynamics now on this hypergraph, I would like to compare with the dynamics on the networks. Once you have an hypergraph, you can have several projections. You can have the projection A on the left, which is a multigraph, where you replace each hyperedge with several links. Or you can have the projection B, which is the simplest one, which is a binary projection, where that is you project every hyperedge of a given size to a complete clique of the same size. Or you can have the projection C, where you take into account the cliques, but also some weights. And in the paper that I showed you before, we show which are the good ways to be assigned. And in particular, this is called equivalent weighted network, because we can prove that the dynamics on this network is equivalent to the dynamic on hypergraph. So we can use all the stuff that we have on network theory to the hypergraph theory. So in the following, I will compare the hypergraph, so the ranking obtained on the hypergraph, so the random walk, with the case of the projected network. There are several things that are interesting. I will focus here on one thing, which is the ranking inversion. As I said, in the top ranked node in the random walk depend on the degrees in the case of network, on the hyperdegrees in the case of hypergraph. So you can have this feature that in the case of hypergraph, in the top of the blue and the red hypergraph, you have that node J is ranked above node I, because its hyperdegree is the largest, 4 versus 3. While once you project down in the clique, the opposite happens. So you have the node I, which is better ranked than node J, because now the degree of I is 3 and the degree of J is 2. So this is indeed quite general. And once you have a data set, you can think of rank the nodes according to two strategies, the one with the network and the one with the hypergraph. So you have two dimensions. And you can realize that there are some nodes, for instance, here, the red nodes, that are better ranked once you take into account the size of the hyperedges. So for this node, it is more important the size of the hyperedges than the number of neighbors, or the degrees. While for the green nodes, the opposite occurs. These are nodes that are better ranked or with respect to the horizontal line, that is the standard random walk processes. And then these nodes are the ones that have larger degrees, but smaller hyperedge sizes. And then there are the blue ones, which are intermediate, and so they can be in some sense in both. So it is important that once you have a database, to choose the good approach to rank nodes if you're interested in ranking, but I'll show you there are some other approaches also interesting. So to go to the conclusion, we apply this to the archive database. Here I show you the result for the HEP, so high energy physics, but we did the same analysis for all the archive. It is important here to show that in the HEP there are 4 subclasses. On the left is the experimental, bottom left is the phenomenological, top right is lattice, bottom right is the theory. And again, I use this 2-dimensional classification where on the horizontal, I put nodes according to the random walk on the network. That is, node more important are nodes with the larger degrees, while on the vertical axis, I put node ranked according to the hypergraph. That is, node top rank node are the one that are larger group. So if you want, you can see that in the experimental, so in the top left, there are a lot of points, these authors that are better ranked with respect to the vertical dimension. That are authors that wrote few papers but with a large group. As the same is true for the phenomenological, that is on the bottom left. And indeed, you can show that using this approach, you can differentiate from the theoretical part where researcher wrote papers in the small groups with respect to the experimental part where normally papers are written by a very large number of co-authors. So this can be observed using the hypergraph, but not using the projection on the network. So I think that with this, I show you the importance of the good framework to use hypergraph to model phenomena where there are high order interaction. Just before to conclude, I can show you that we did the same analysis for the classification. We show indeed that if you use the hypergraph, you can better classify, here is the case of animals, instead of the standard projection on the network. And more recently, we also use this approach for the community detection. We show that using the high order interaction that is present in the hypergraph, you can better represent the community structure of the data instead of the simple projection. To obtain this result, we use the Markov stability framework that has been developed in case of network. But again, if you recall the projection C, where I show you that there is a orbital equivalence between the dynamics on hypergraph and on the projected network, we can use all the machinery developed for networks, in particular the Markov stability framework, to develop the same idea for hypergraph. And so with this I finished, and I thank you for your attention, and welcome for any question. Thank you very much.
Okay, thank you very much, Theo. Okay, we have, I guess we have time for a couple of fast questions. How can we do it? So if you want to ask it on the chat or you want to raise your hands?
I have to unshare because otherwise I cannot read the chat.
Okay.
Okay, now I unshare. Okay, so I can read the chat, but I don't see any question on the chat.
Well, we don't have no questions. So I don't know how to manage this. Okay, now we have by Johan Dubelom, you have a question. When is a hypergraph description better?
Okay, so it depends also from your research question. In the case of authors and papers, if you want to take, if you want to take into account that you are mixing authors that are from different research fields, where you have some fields where you have more papers written by few authors, and in another research fields when you have papers written by a large group of authors, it will be difficult to compare both. But using our ideas of the 2-dimensional classification, you can see in some sense which is, I will not say not the best, but which are the differences in the two groups. And then you can say, okay, this author is better ranked because he's part of this group of research, while this other is better ranked because he has a less publication but with a larger number of co-authors, and so is better in the other. The same is the case of classification of the animals. Take into account the high order dimension of the feature of the animals, you can obtain a better classification that if you project on the network, on the click network.
Thank you.
Okay. If we don't have more questions, so I think would be okay. Do you have computational problems using hypergraph?
Not yet, because the hypergraph, if you think of the metrics that I introduced at the beginning, the adjacency metrics are exactly the same size of the nodes, so the squared number of nodes. So it's the same case of the network. So if you have a network with 1,000 nodes, you have the same adjacency metrics. Then if you use the incidence matrix, is the better, because then you have a sparse matrix, and then you can save a lot of space. So the computational difficulty is the same as network. For this reason, I prefer this to the simplexes where you need tensor. Here, you don't need tensor, you just work with matrices.
Okay, then the last question. So could you show the slide with different representations again?
Okay, so let me share again.
Probably, Panos, all these sessions will be recorded, right?
Okay, so you mean this one? Because I cannot read anymore the question because I'm
yes. He says yes.
Okay, so on the top right, you have the hypergraph where I put in color the hyperedges, and then you have the incidence matrix. Then you can project on your left, so the A, you have a multigraph, because now you replace, sometimes you add a links, but you add as many links as the number of nodes inside the same hyperedge. In the projection B, you lose this multigraph structure, but you only use the fact that two nodes belongs or not to the same hyperedge. So if you have 4 nodes, then you add all the 4 links among the nodes. On the projection C, you have a network, but now you have a weighted network, and in the paper we show which are the good weights in such a way the dynamics on the hypergraph, so the random walk dynamics, is exactly the same dynamics on the weighted network. And in this way, we can use all the machinery for the network theory also in the hypergraph.
Okay, Timoteo, thank you very much for your presentation. Also for okay, I think we have no more time for questions. Sorry.
Okay, thank you very much.
Probably you can answer this later on the chat.
In the chat.
Okay, let's go to the next. Thank you very much, Timoteo. So let's go now to the next speaker, Oriol, please.
Hi. So I'm going to share my screen. Let's see if it works. Share. Okay, so I'm clicking play. Let's see if it works. Good afternoon, everybody. I'm Oriol Artime, and I'm working as a postdoc in Fondazione Bruno Kessler in Trento, Italy. And today I'm going to present the results of a paper that we published recently with Manlio and Domenico, and they are about how non-local cascade propagation can lead to discontinuous phase transitions in multiplex systems. So in general terms, in this work, we will be dealing with the problem of robustness. That is, we ask how good a system is at handling perturbations that might affect its functionality. And in particular, we're going to focus to a structural robustness. That means that we have a structure and we remove a part of this network and see how the functioning of the network changes. An hypothesis that we work with is that the connectivity and the functionality of the networks are closely related. In particular, that connectivity is the first proxy to assess functionality. That means, for example, that if we have a network with a single connected component, that network is fully operative. And if some small parts of these networks are removed, the functioning of the network is barely affected. But if this network is split in many small parts, then the functioning of the network is really hindered there in this case. And the simplest conceptual way to study network robustness is by means of percolation. In the process of percolation, what you do is you take the original network, remove a subset of nodes, and you compute several different geometrical and statistical properties of the remaining network. A more realistic way to assess structural robustness is by assuming that this perturbation can propagate, and the simplest model that allows mathematical tractability is the propagation of the information or the failure via first neighbors. But there is an even more realistic way to assess the structural robustness that, however, has been much less studied, and is the non-local propagation of failures, meaning that one node might fail in one part of the network, and as a consequence of this failure, another node far away from this first failure also fails. Some examples in real systems of this non-local propagation of perturbations has been, for example, the disturbances in the North American power grid, or in the air traffic disruption in 2010 of the Icelandic volcano. Well, after this introduction, here is what we want to achieve in this work. We want to characterize the effect of non-local cascade propagation of failures as a function of several multilayer properties. And before going to the results, let me make clear what we understand by a cascade. Cascade is a process that has a non-additive dependence on neighbors, meaning that in some cases one of your neighbors fail and that makes you fail, and in other cases you can be surrounded by neighbors failing and then you can still be operating. It is a process that propagates non-locally, and it is a process that can have system-wide effects due to very small perturbations. So, and we say that we study this in multi-layer networks. So just as a reminder, that multi-layer networks can be regarded as a collection of networks in a layered structure, where each layer can be considered as a context of interaction. So now let me introduce the model, a model that can explain this non-local propagation of perturbations, which is the following. So let's assume that every node has a load, which is the number of shortest paths crossing the node, and has a capacity, which is proportional, and it's a fixed quantity. It's proportional to the initial load. The proportional factor is called the tolerance, and is this parameter alpha. And if for whatever reason the load is higher than the capacity, then that node fails and it is removed from the network along with all its links. For example, look at this sketch. Let's focus to this central node. The initial load is 3 because there are 3 shortest paths crossing the network, but then a node fails. The shortest path between this node and this node now is over here. So now the load of this node is increased by 1 unity. Let's say that now the capacity, the load is higher than the capacity, then the network has suffered an overload failure. And this can cascade can propagate in a cascading way, failure after failure. So I said that we want to analyze cascades in multi-layer networks. So these rules need to be adapted for this type of topology. So we assume that both the interlayer and intralayer links contribute to the load, and that when a node fails in one layer, then the replicas of that node also fail in the other layers. We simulate this process and obtain this. So here I'm plotting the size of the largest connected component of the network once the cascade has stopped as a function of the tolerance parameter. And here in this plot and in all the other plots of this talk, I'm focusing in the initial condition where we remove a single node and we pick the node to remove the one that has largest load. So when S, with this mean size of the largest component, is close to 0, it means that the cascade completely destroyed the network. Instead, when it's close to 1, it means that the network is left almost untouched. The more this curve is located to the right, the less robust is the system, because it means that there is a larger range of tolerance values of alpha that for which then the network can be dismantled. And something curious from this plot is that the error bars in the central area seem quite large. And this has an explanation if we, instead of looking at the mean size, we look at the entire distribution of largest connected components once the cascade stops. We see that the distribution is unimodal and close to 0 for small values of the tolerance. When the tolerance increases, then a second peak develops close to 1. And if we keep increasing the tolerance, the first peak vanishes and the second peak dominates. And this looks like a discontinuous phase transition. And actually, if we go to, we calculate the Binder cumulant, this quantity becomes negative in the critical region and tends to minus infinity as the system size increases. The system size is the size of the network. And well, if you are, so this further proofs shows that we are dealing with a discontinuous transition. But if you're interested in the article, we show other methods. So we prove that we numerically prove that this phase transition is it's quite robust, it's discontinuous, and it's not as a finite size artifact. So now that we know what type of transition we have, we ask how to make them then our network, our multiplayer network, more robust. And we work with the following hypothesis. That is, when the extra load of a failure is homogeneous, it can be homogeneously redistributed across the network, then the cascade cannot propagate so easily. So increasing the average path length L, then we will observe an increase in the robustness of the system. And there are different mechanisms, simple different mechanisms that can modify the average path length of a network. One mechanism is to decrease the average path length, for example, by collapsing the multiplex structure onto a single layer where all links are projected there. Another way, for example, is to increase the number of layers in the network. And then a final mechanism is related to the multiplex parameter Q, that is the fraction of nodes participating simultaneously in the layers. But in other words, the nodes that have replicas across layers. So when this Q, this fraction of shared nodes is low, there are few nodes acting as bridges between layers, and when the multiplexity increases, then the connectivity between layers increases as well, resulting in a decrease of the average path length. So here I'm checking that this hypothesis is verified for the three mechanisms proposing aggregation. Here, you see the aggregation is it's on the left of the multi-layer structure. Also increasing the number of layers, we see that as you have more layers, these curves, the order parameter of the transition tend to the left, and also here increasing the multiplex parameter. So we show that the robustness increases if the average connectivity between nodes increases. So to conclude the talk, now I want to focus on how these results are verified in an empirical network, because here the networks are synthetic, so they don't have correlations. And I take here the European air transportation network formed by 37 layers corresponding to different airline companies. Note that now in each layer we have networks of different size and different degree distributions, and with the topological correlation within layers, also correlations across layers, etc. So even in this case, even in a network with these characteristics, we confirm that qualitatively we are obtaining the same results as in the synthetic networks. So with this, I want to conclude my talk. I just want to give you some take-home messages. The first one is that load capacity models, as the one presented here, can be used to model the maybe most realistic propagation of cascades, which is the one of non-local propagation. The second message is that multiplex networks exposed to overload cascades display a discontinuous transition. And the third one is that a plausible way to increase the robustness of a network is to reduce the average distance of a node. And here I showed different mechanisms that do this reducing of the distance. So with this, I want to conclude. Thank you for your attention. And if you're interested in the reference, here you can find the paper. So thank you so much.
Okay, thank you very much, Oriol, for your presentation. So let's turn to the audience to see, do you have any questions? Okay, then Shaunak has a question. Can I read it for you? So it's, does the structure of the network make any difference in cascade phenomena? The structure of the network, probably, which is
so if you
model.
if you mean the type of network inside each layer, so if we are not considering different correlations across layers, so if we change the type of topology inside the layers, yes. So it is known that so I didn't say it, but we are considering scale-free networks inside the layers. So the distribution of loads initially is very heterogeneous, similar to the degree. So when you have, for example, an Erdos-Renyi network, for which the distribution of loads of shortest path is not like a power law, doesn't fall like a power law, then you don't observe these cascades. Yes.
Okay, second part of the question is, what are the sizes of the networks used in the simulations?
So yeah, when we did the finite size scaling, so we computed the transition up to several like I think like 30 or 40,000 nodes per layer. Yeah, per layer, but for the finite size scaling. These were quite heavy simulations, and for most of the plots we used like several thousand nodes per layer only.
More questions? Okay, I will ask one myself.
Yes.
And now you were saying that you have this scale-free network. Did you consider correlations in the sense that degree kind of a degree correlations among the layers or something of this sort, or just no correlations at all?
No correlations at all, but it's certainly a very interesting question, and we want to look it in the near future, of course. But yeah. At this point, it was just a paper to characterize this non-local phenomena in multi-layer networks and see the type of transition, how to characterize it. Yeah.
Okay, thank you very much again. Let me check. Okay, thank you very much again for your talk and for answering the questions. So now we have another talk by Sebastian Raimondo. Are you around, please?
Yes, I'm here.
Okay, you are here. Good, good. So please go ahead.
Okay, I have a pre-recorded video, so I share it.
Okay.
But I see that I have not the permission to.
Okay, let me check. Let me check if I can do it.
Okay, thank you.
I don't know if I have all the rights. Okay, now you are.
Now you are co-host. I made you co-host. It's okay.
Okay.
Yes, okay. Now I can do it.
Go ahead.
Okay. You can see my big face?
Yes.
Okay.
Yes, fine, fine.
Hello, everyone. I am Sebastian Raimondo. I am a PhD student in mathematics at the University of Trento in Italy, and I work in the group of Professor Manlio and Domenico at Comunelab. Let me share my screen, first of all. Okay. So, first of all, I would like to thank all the organizers for giving me the opportunity to participate at this conference and to present my work conducted together with my supervisor, Manlio and Domenico. Here is the outline of my presentation. First of all, the motivation and our research question. Then I will briefly introduce the state of the art before presenting our framework for a new definition of the topological descriptors of complex networks. And before concluding, I will present some results from numerical experiments. So our goal is to find a simple and effective way to define the structural features of a complex system when the network structure itself is uncertain. We focus in particular on networks of dynamical systems, so those systems where the nodes have a time-dependent state. In this setting, currently, the structural features can be analyzed after the reconstruction of the entire network of relations. The idea is the following. Imagine to have a real system that consists of many subsystems interacting with each other according to the network structure that is actually unknown. So in the figure that you see here, for example, the dotted edges cannot be directly observed. Instead, the only information that we have are measurement of the dynamics. So we have only the time series, like the one that you see in the figure. From this time series, we need to reconstruct the structural relations in order to compute the topological features of the network structure. To reconstruct the network of relations, the most used method consists in computing some measure of relation between the nodes, like pairwise correlations of various types, the mutual information or other causal measures. And in many cases, these measures are compared with null models to perform statistical tests and eventually obtain p-values. In any case, the pairwise outcomes of this procedure for all the couples are rearranged in a connectivity matrix, like the one that you see here, in which the entry ij corresponds to the value of relation between subsystem I and j. According to the method employed, this matrix is then thresholded, and all the values below the threshold are set to 0 and the other to 1, so that we end up with a binary adjacency matrix and consequently a binary network. And the reconstruction is done, basically. But given the arbitrary nature of the threshold, the results are affected, of course, by errors of different types, and also the uncertainty, most of all, is ignored. Other methods are available, such as those based on the Bayesian framework, that are very powerful, but in most cases, an underlying generative model is needed, while these methods are model-free. After the reconstruction, the topological descriptors can be computed starting from the local ones, such as the degrees, until the global ones, such as the number of components and so on. With our work, we propose a change in the point of view on this problem. Instead of applying a method to reconstruct the entire network of relation, we propose to use a different representation of the network structure, which we call it fuzzy network, to compute directly the topological descriptors. Let's come back to the previous real system that is still unknown. We have the data coming from the subsystem, and with this data, we want to compute not just the measure of the interaction, but also the probability of those interactions. The computation of these probabilities is mostly a problem-specific task. And in some cases, the probabilities comes as given data. In other cases, are the results from other models, or can be obtained directly from observations. Sometimes also the above-mentioned Bayesian methods can be used. In addition, in our paper, we propose a simple method to obtain, with a closed formula, a posterior probability of existence of the edges, given the p-values computed with the most used method for network reconstruction that I showed you before. In any case, these probabilities can be organized again in a matrix, which seems again as a weighted adjacency matrix, but now it has a very particular meaning since it represents the probability of existence of the edges. This matrix is the formal representation of the protagonist of our approach, that is the fuzzy network. This is a probabilistic model of the structure of our system that can be represented as a complete network whose edges might exist with a certain probability. From this starting point, we want to define the structural characteristic, the structural features of the network. But given the stochastic nature of this structure, all the structural descriptors in turns, starting from the degree, the clustering coefficient, and so on, must be redefined as random variables. So instead of having a unique pointwise indicator, we will have an entire distribution for each descriptor. So let's see what happens to the simplest one, that is the degree of a single node. Traditionally, this is simply the number of edges incident to the node. The probability of existence of the edges here correspond to a single row or column if the network is undirected of the probability matrix. So from this point, we have our fuzzy network, or fuzzy node in this case. It is to be noticed that now it doesn't even make sense to ask for the degree of this node, because this node has all the possible degrees at the same time, each one with a certain probability. So we obtain a complete degree distribution for the single node degree. We derived also the analytical form of this distribution that is highlighted in red here. And I don't go into details here that you can find in the paper, but I want just to notice that having a probability distribution, we are provided with much more information than the simple degree. And this additional information, of course, is about the uncertainty of the descriptors. We can extend the result to an entire network, like this one, and calculate the degree distribution for every node, and you see the distributions in the plot on the right. And also the mean value, the expected value of the node degree in the table below. If we imagine now to apply, for example, as before, a threshold, we would obtain slightly different values for some of the nodes. But for example, in the node 3, in this case, the node 3 turns out to be isolated. While if we look at the distribution, we see that the probability of having degree 1 is more than twice the probability of being isolated. And this is an example of the implications that this probabilistic perspective offers. After some calculation, it can be proven that the probability, the expected degree for the entire network is given by this formula, which is twice the sum of all the probabilities divided by the number of nodes, which is structurally very identical to the average degree of the classical node, classical network. In a similar manner, we can compute the probability distribution for another important descriptor, that is the clustering coefficient. In the plot, you see again the probability distribution for the clustering coefficient for each node. And as you see, the probability distribution in this case has a very irregular shape. On the bottom left, you see again a statistics computed from this distribution and a comparison with, again, a threshold and network, just like before. And again, we can appreciate the difference between the two methods, since for the node number 4, for example, we have that the probability of having degree 0.33 is almost 4 times the probability of having the value given by the threshold. So it is in this sense that the analysis of the topological features can be more robust against the uncertainty. Another important network feature is the connectivity. Now, we are asking for the probability that a network of n nodes consists of a single connected component with k existing edges. And here you see the probability distribution which answers this question. And it deserves a comment, because as you see, it seems that adding more edges in the network makes the probability of connect the network smaller after a certain point. It seems counterintuitive, but the reason is the following. In the left part, we do not have enough edges to connect the network, and indeed we need at least n-1 edges to do so. Then the probability becomes positive and has a peak, and then it drops down. This is because having a network with many links is unlikely, and consequently is unlikely to have a connected network with many links as well. So it is a sort of trade-off. Other descriptors can be redefined in this way. And you find some more in our paper with also some other details. Lastly, just a rapid glance on the numerical experiment. We tested this framework using a large set of synthetic network of 3 different types with 5 realizations each. And on those networks, we ran a linear and a nonlinear process, an Artime logistic process with 5 different parameterization each. Then we computed the p-value using the null model for 5 different well-known connectivity measures, and so the probabilities. I cannot go into details here because of time constraint, but you find all the comprehensive explanation in the paper. And basically, this plot shows the result for the degree, the clustering coefficient, and the comparison with the threshold approach with different level of the threshold. Here I reported just an aggregated result which shows the comparison in the median value of the degree of the clustering and the clustering coefficient with the real values of the networks. So in conclusion, from a probabilistic model of the structure, we defined the topological descriptors of a complex system, keeping information about the uncertainty until the end of the process, without an explicit reconstruction of the entire network. In the future, this work can be extended in various ways, for example, to other descriptors and to the mesoscale structural features. In addition, the fuzzy representation of the network can be also used to investigate the dynamical properties of the networks, studying, for example, the spectral properties. And this, with this, I finished. I will be happy to answer your question. Thank you for your attention.
Okay, Sebastian, thank you very much for your talk. It was a very interesting topic. Let's see. Do you have somebody in the audience having any question? Let me check because really? Have you applied in real data?
Okay. Yes, partially, yes, because we used some structural, some data about structure. For example, the brain of a species of macaque and a structural network of social relations. And we ran some dynamical models also in those cases and obtaining similar results as the ones that I just shown you. And you will find these results. Yes, there are 3 different real world network structure with which we perform our analysis.
Hello, everybody.
Hello, Axel. Okay, you can make a question.
No, sorry. So, so I was scheduled for a talk, so I was a bit late. Sorry.
Okay, no problem.
Okay, any other question in the audience? Let me check because this is not easy. So we have, oh yes, we have, how does your method compare with Bayesian methods?
Well, to do a comparison with the Bayesian methods, we would have to construct, to build an ad hoc probabilistic model for the structure, let's say. This is not our aim because we do not want to reconstruct the entire network of relation, but just to keep the information about the network features. So this to make this comparison, we would go much over this topic, let's say. We would need to build a probabilistic model to do so. So we can, in a model-free perspective, we cannot do it, let's say like this. I don't know if I answered the question.
Yeah, there is another question. That how heavy are the computations compared to normal correlation networks?
Okay, the computations are quite hard, let's say. But given that many of these descriptors relies on the probability distribution that I've shown you for the degree, that is the Poisson binomial distribution, that is not the binomial, is not the Poisson, but is another kind of thing. And for this distribution, there exist many computational methods and efficient computational methods to compute this distribution. And so the computational effort can be reduced thanks to this efficient method for the computation of this particular probability distribution that returns many times in the calculation of different topological descriptors.
Okay, so it seems that we don't have any more questions. No, so you have 3, 2, 1. Okay, so Sebastiano, thank you very much again for your talk and for your answers. I think it's really very interesting topic to take, because it's quite involved, this of course of looking at correlations and trying to binarize networks. So thank you. And now we go for next speaker, who is Alberto Aleta. So Alberto, are you ready?
Hello. Yep.
Okay.
Let me share the screen. I have it recorded here. Okay.
Okay, that's it.
Thanks for stepping by. I'm going to talk about data-driven contact structures from homogeneous mixing to multi-layer networks. In this work, we are interested in studying the transmission heterogeneity of the population. We could consider two types of heterogeneity mainly, one that would be more biological or environmental, and that essentially modifies the individual's infectiousness, but we are not interested in that one. In this work, we are interested in the contact patterns of the population, that they essentially depend on the behavior of the population. As we know, each individual behaves in a completely different way. This completely changes from city to city, to region, from country to country. So this is fairly complex to study, and we also require a lot of data. The first epidemic models were introduced in the early 20th century, and they consider a very simple approximation. They just consider that the population was completely homogeneous and that everyone behaved the same. They just assumed that each individual would contact a certain number of other individuals, and this was encoded in just one number, the average number of contacts. As we have here in this quote by McKendrick, we can see that they considered that infection depended on the collision between an infected and uninfected animal. So they had this picture in mind of all the individuals being in the same planes, just moving around and spreading the disease without any heterogeneities. Then, by the end of the 20th century and the beginning of the 21st century, networks were introduced in epidemic modeling. So there is this very interesting result by Pastor Satoras and Vespignani, where they showed that the epidemic threshold depended on the average connectivity of the network, and also on the second moment of the distribution. This was especially important because for certain types of networks, like scale-free networks, this tends to infinity, and thus the epidemic threshold tends to 0. But note that the amount of information that we need to build this model is much higher. So ideally, we would have the exact degree, so the exact number of contacts that each individual has, or at least we will need the distribution. But still, a distribution is much more than having just one number as we did before. In any case, this idea of introducing heterogeneity was not completely new. In the 80s, slightly before also, there was the idea of introducing selective mixing. So it was to consider that certain groups of the population will tend to interact with those groups and will interact differently with other groups. This was particularly important in the transmission of sexually transmitted diseases, where they observe a high degree of heterogeneity. And also there was this empirical observation that there was a virtual absence of a threshold for disease agent persistence. Then, as we can see, it's essentially the same result as we saw before, but this was just an empirical observation. It was not proved. But still, they built models in which they took into account these kind of groupings, and they found things like this. So here, what they have is the sexual activity of individuals. So this I is not the degree, but the sexual activity. But you can see that this is essentially the same result as in the previous slide. But we've reached here from very different perspectives. So in the other one, if you remember, in a network, you consider that each individual has a certain degree, and then you say, okay, every individual has a certain number of connections, but I'm going to assume a mean field approximation where individuals with the same connectivity will behave the same. So essentially, you are going from the individual to the group. And here we are going the other way around. So we have an homogeneous population, but we say, okay, but certain individuals will behave in a group way, or we can capture them in small groups, and we'll reach the same result, obviously. But the point here is that they didn't have the data to estimate these things properly. Actually, another type of grouping can be done with age. This is just to consider that individuals, for example, children, tend to interact more together. Adults tend to interact with other adults. Of course, they interact also with the elderly, but those are different groups. Data about these contact patterns were not available until the 2008. So we can see that we had to wait almost a century since the first epidemic models were introduced until we actually have a little bit of data about the heterogeneities of the population. Our proposal in this work is to join these two sets of data, these two approximations, and build a multi-layer network. So now each group will belong to a specific layer, but we will also take into account the degree of each individual. So in this way, we are adding all the heterogeneities that we can. So not only we take into account that a certain individual might have a lot of contacts, but we also take into account that those contacts will probably be with individuals of the same age or close enough. Again, we need a lot of data to build these kind of things. But how do we do this? Okay, so we consider that suppose that you have a node and there is a stub going to another layer. So we say that the probability that the stub going from layer alpha to layer beta is given by this equation. This thing here is the age mixing patterns. So this is essentially a matrix. And then we also say, okay, once we have a stub in this layer, what's the probability that the stub will go to exactly node J? So is this expression here that, as we can see, depends on the degree. Now we join these two things and we obtain this expression. This expression needs a lot of data. One is the age distribution of the population. This is widely available. This is usually not a problem. Then we also need the age mixing patterns of the population. Every day there are more information about this, but still it's quite scarce. And then we also need the number of contacts of the individuals to obtain the degree distribution. These two sets of data usually come together, but not always. Sometimes you only have the matrix, other times you only have the distribution. But in any case, if you're lucky enough as to have all the data, then you can use this expression to build a network in which you take into account both the age and the the degree of individuals. But there is a thing here. So we know that in the age mixing matrices, there is a reciprocity condition. What is a reciprocity condition? Well, it says that the number of links going from, in this case, group alpha to group beta has to be exactly the same as the number of links going from group beta to group alpha. Since these groups not necessarily have exactly the same size, we have this condition here. Okay. The point is that if we include this condition, we see that for this to be true, there has to also be fulfilled this thing here. So the average degree in each layer is determined by the age mixing patterns of the population. So this is essentially what is joining the two things. They are not completely two different things. We don't have the age in one side and we have the degree in the other, but we have both things closely tied together. So why is this important? Okay, so we explored this firstly in an SIS model. Here, let me explain you a little bit the legend. H means the homogeneous mixing approximation. M is the H mixing matrix. Then C is the network. And CM is where we take into account both things, the network and the mixing matrix when we build the model. So first, let's focus on the epidemic threshold. This is the transmissibility. As you can see, for the homogeneous mixing, we have this epidemic threshold. Once we start to add more heterogeneity into the population, the epidemic threshold tends to fade out, as we knew from network epidemiology. On the other hand, if we focus on the prevalence by age group, here we are considering a scenario where more or less the prevalence is the same for the whole population. It's around this point, okay, regardless of the model. But we can see that, okay, the total number of infected individuals is the same, but it's distributed in a very different way. When we just consider the network, we have no difference between age groups, as expected, because we are not taking into account age when we build the network. But for the other two, either just the matrix or the multi-layer scenario, we get mostly the same shape. So this is telling us that, okay, this multi-layer model is really good, but we need a lot of data to build it. So if we don't have that data, not everything is lost. Maybe just using the matrix would be enough, but not just using the network. On the other hand, for the epidemic threshold, again, if we have the multi-layer network, that's great. But if we don't, at least we need the network. But the H-mixing matrix would not be enough. Next, we focused on studying the basic reproduction number. This was just a very simple experiment. So we essentially started simulation with one infected individual and measure how many infections that individual produces. And as we see for the network scenario, we get essentially the same result for all age groups as expected, because again, we are not taking that into account when we build the network. But for the multi-layer scenario, we get very different results. So this is telling us that it's really important to take into account age when we are trying to measure these kind of things. And lastly, we see, okay, how would vaccination be modified in each of these scenarios? So first, we try to mimic a real situation. So this network has been built with data from Italy. So we try to vaccinate the population using the data from Italy, that essentially mostly the elderly are the ones that are vaccinating. That's why in this standard vaccination, the attack rate for those kind of individuals is lower. And we say, okay, let's just increase by 1% the vaccination and apply it randomly. Note that we are talking here about 1% of the population. Normally, 10% of the population is vaccinated, so 1% is a good amount. And we see a homogeneous reduction for all the models. But we say, okay, now that we have a lot of data about individuals, let's try to be wiser and let's try to target the vaccination. So how do we target that when we only know the age mixing patterns? Okay, we target the group with most activity, that in this case are the young individuals. That's why the reduction is really large there. Note also that this already is much better than the random vaccination. But still, if we now go to a network, we obtain a much higher reduction. Here we are essentially vaccinating the hubs, and as we know, that has a huge effect on the epidemic, on the network. However, when we do the same in the multi-layer scenario, we don't get essentially the same result as in the network. And why is that? Okay, it's because we have a lot of correlations. So in a simple network, you have two hubs, and if you build it properly, there are no correlation between those hubs. But in this case, we know that individuals with a lot of contacts tend to be young, and young individuals tend to interact with each other. So there is that effect that first, hubs are constrained in certain layers, and also the effectivity of vaccinating one hub is not that high because it's probably connected to other hubs, and thus the effect is not that large. We can clearly see this effect if we take the multi-layer network and rewire it. We recover the result of the simple network. So essentially, when we destroy correlations, we obtain the result of the previous network. So the conclusions. Models depend on the availability of the data, and different heterogeneities produce different effects. We've seen that for the epidemic threshold is better to work with networks. For the prevalence by age, it was the age mixing patterns. And for vaccination, it's really important to take into account both. But not everything is lost. In the absence of data, we can use simpler models. But it's really important to be aware of their limitations. So that's all. Thanks. You can check out the paper. And if you have any questions, yes, you can send me an email. Thank you.
Okay, Alberto, thank you very much for your talk. Do we have any questions in the audience? No questions?